Hi, I'm Jann Müller. I'm in charge of the Plutus applications team. I'm going to show you the new version of the Plutus Playground that's been released today. The Plutus Playground is an online tool for testing and editing Plutus contracts. It has a code editor for writing contracts, and it also has a simulator for running them that doesn't require any code. And we're going to look at both parts in this video. First of all, when you load it, you'll notice right away that the look and feel of it has changed quite a bit compared to the last version. And we have put a lot of effort into improving the user experience and making it a better and more powerful tool to use for writing serious contracts, not just toy examples. So one aspect of this is that we now have key bindings in the editor, and you can choose between Vim and Emacs and default. Default is the Visual Studio Code key bindings, I believe. You can jump to lines, skip words, and so on. So it's much easier to use the code editor, and it's more, closer to a real offline editor than it was before. At the top, you have a number of samples that are included. We're going to look at a couple of them and run them in the simulator. Let's start with the Hello World contract. That's a very simple one. It only prints out a log message and doesn't do anything else. And with all of these samples, when you load them, you can click Simulate right away. So normally, when you enter some code in there, you have to click the compile button, and it sends the code to the backend for type checking and for the backend to recognize the interface of the contract. But with the samples that are included, you don't need to do that. And the simulate button is enabled right away. And if we click it, we get to the simulator view. And that's where you build up the simulation that uses the contract. And this simulation has multiple agents that work together and that submit transactions to a simulated blockchain using your contract over a period of time. And all of the examples here have a number, they all have one or more simulations built in. And that's what this tabbed interface here is for. So the Hello World one has a single simulation built in, which is called Hello World. And that simulation, the built-in one, is shown here at the bottom, where it says Actions. Now we can see that the Hello World simulation only has a single step, wait for one block. So we don't have to edit anything or change anything. When we load any of the built-in simulations here from the samples, we can click simulate, and then we get to this page, and we click evaluate right away, and it will send the code of the contract and the actions that we've defined to the server and show us the outcome. So it's also very nice to use just to see what does the contract actually do, even if you don't want to change anything or you don't know how to, what kind of Haskell statements you need to do any fancy contracts. You can look at the examples that we have and see what they do just by clicking on evaluate, and you'll get to this page. So the transactions page shows the outcome of the simulation. First of all, we have a blockchain, which consists of a number of blocks. And in this case, there's only a single transaction here, because the Hello World simulation didn't do much. And in every simulation, we always have this initial transaction, which happens in slot 0 and creates the initial funds that the simulated agents use. And for the Hello World simulation, there are two simulated agents. One is called Wallet 1 and one's called Wallet 2. And each of them gets 100 Lovelace in the beginning. And that's what this initial transaction does. So we can see the outputs of the transactions on the right-hand side. And the initial transaction here is special because it doesn't have any inputs. And that's the only transaction that's allowed to create new ADA. So that's why it has a forge field here below the transaction details saying that it created 200 Lovelace. And no other transaction is allowed to create values of the ADA currency. It is possible and easy to create your own custom currencies with the multi-asset ledger. But ADA is the native currency, and that can only be created by the initial transaction. Then we can see what the final balances are of each of the agents that participate in the simulation. So we selected the first transaction, and the table here shows us the balances carried forward after this transaction. And we can see after the transaction, each of the two agents has 100 Lovelace. And the chart here shows the final balances in different currencies. And we only have ADA, we don't have any custom currencies in this simulation. So we get 100 ADA each. Now the interesting bit of the Hello World contract is the logs. And here you can see all the noteworthy events that happened in the simulation, ordered by time. So first event that we see, and that's going to be the same every time, is validating transaction, and that's the initial transaction here. And then this is the end of slot 1. And now we're currently in slot 2. And in this slot, two things happened, because both contract instances produced a log message. And we had so in this simulation, we have two agents, wallet 1, wallet 2, and therefore we're running two instances of the contract. And because the Plutus application is a distributed app, it runs on different machines. It has, on each machine, it might have its own state, and all these parts, these distributed parts, they communicate via the blockchain. And that's why in the logs, we can see the logs for each of those simulated agents. So you can imagine that there are two computers, wallet 1, wallet 2, and a third one, which is the node with the blockchain. And they're all being simulated by the simulator. But the Hello World app, as such, it doesn't actually produce any transactions, so we don't see any other validating transaction messages. All we see is the logs that are produced on the user's machines. It doesn't interact with the blockchain at all. Well, let's go back and change the simulation a little bit. So we have the action sequence at the bottom, and up here are the agents that we simulate. And we can see wallet 1 and wallet 2 here, and we're going to add a third one, wallet 3, and wallet 3 is going to get 1,000 Lovelace because they have more money. So now we evaluate again. And see the results of this simulation. The initial transaction has 3 outputs now, and we can see that wallet 1 has received 1,000 Lovelace, just as we specified. And now if we scroll down to the logs, we can see that there are 3 log messages, because the app is running on 3 different systems, basically. And that's important to remember about Plutus contracts. They're not just pieces of code that run on the chain, but they're also, to a great part, pieces of code that run off-chain on different machines. And that's what the simulator is showing us here. So we've got Hello World from 3 different wallets. Now let's look at a more complex example. Vesting. So the vesting contract, it locks some funds in a script output and they have to stay in there for a certain amount of time before the receiver of the funds, the recipient, can take them out of the script output. So it's like a trust fund in a way. They just have to stay in there for a while. And again, the vesting contract is a built-in contract, so it has the simulate button is available right away. And if you click it, we get to the simulator page, and it is already, it comes with the built-in simulation that we see at the bottom. And in this case, it's a bit more complex than the Hello World one. So we have 6 actions altogether. And now the actions that we see, they're contract-specific actions. So previously in the Hello World example, all we could do was wait for things to happen and make payments to other wallets. But now, in the vesting contract, we have additional actions that we can do, that the agents can do. And these are defined by the contract. And we can see in the tabs, so the boxes here of the wallets, that they have a retrieve funds and the vest funds button. And in the definition of the contract in the code, we define which endpoints we want in the contract. So in this case, retrieve funds and vest funds. And we also define what the input types are for these endpoints. And in the simulation here, we can see that the vest funds endpoint doesn't have any input at all. It's just an action, basically. We say, okay, now let's vest the funds, let's start the contract. And that's what happens at the very beginning. Then we have a wait action where we wait for 20 blocks, which is the amount of time that needs to pass until the funds can be retrieved for the first time. And after that, wallet 1 calls the retrieve funds endpoint. And here there's a form input to give the value that the retrieve funds endpoint expects. And because in the Haskell code we define retrieve funds to request an ADA amount, it automatically generates this form here where we can put in how many Lovelace we want to take out of the contract. After that, we wait for another 40 blocks, and then we can take out the remaining funds, which is 4 Lovelace, and we have a final wait action to give the simulator enough time to validate this final transaction. Now let's evaluate this sequence. Okay. So the blockchain now is an actual chain of blocks, not just a single block. We have 4 transactions altogether. The first one, initial transaction, that's still the same. As usual, it creates all the ADA that we're going to use in the simulation. Next one slot happens in slot 1, and it's the first transaction in this slot. And this one actually has an input. So it takes the public key output from wallet 2 and spends it. And where do the funds go to? So there were 100 Lovelace in it. Where do these 100 Lovelace end up? That's on the right-hand side. 92 of them go back to wallet 2, and 8 are locked in the script. And that's a new type of output. So we have public key outputs and we have script outputs that are going to be added by Goguen. And we can see here that this script output with this particular hash locks 8 Lovelace. Now, the next transaction happens 20 slots later. So if you remember, we had a wait action for 20 slots. And during this time, nothing happened. And then we called the retrieve funds action or endpoint. And that caused this transaction here to be submitted. And this is a transaction that spends the script output. So we have the script output here on the left with currently 8 Lovelace in it. That's completely spent. And where do the funds go to? On the right-hand side, we can see that 4 of the Lovelace go back to wallet 1, and 4 have to remain locked in the script. And this is the first time we take money out of the vesting contract. And the way that the vesting contract is defined, it actually has several tranches. So I think after 20 slots, you can take out half of the amount, and then after another 40 slots, you can take out the remainder. So it's sort of staggered in a way that you can retrieve the funds. And that's why some of it has to stay in the script. So even though we spend the entire script output, there's a new script output here, the same address. If you compare the hashes, they're the same, that locks the remaining funds. And in the script code, we check that we don't take out more than allowed, and that we check that the remainder of the funds stays in the script. And then finally, the last transaction happens at slot number 61. So after another 40 slots have passed, we can take out the remaining 4 Lovelace and give them all to wallet 1. And the vesting contract, the definition of the vesting contract also includes who can actually retrieve the funds. So in there it says wallet 1 is the owner of the vesting funds. Final balances, we can see that wallet 1 has 108 Lovelace and wallet 2 has 92, because wallet 2 paid the original 8 Lovelace into the scripting contract. If you go back one transaction, we can see that the balance is carried forward here. It now includes the script address. So any script that we produce is going to be included in this table here. So we can always see at every step on the blockchain, we can always see what's the total balance at each address. And in this simulation, we have 3 addresses on the blockchain. They all add up to the 208 that we had in the beginning. Okay, now let's look at the logs. We have the validating transaction. That's the initial transaction that created all the ADA. The instance for wallet 2 receives the call to start the contract. So that was the first action in the simulation. And we have another transaction being validated, and this is the first of our vesting transactions. So that's the one that locks the 8 ADA. And then we have a lot of slots where nothing happens till slot 21. And then here we have a message from wallet 1 saying, okay, so the retrieve endpoints, the retrieve funds endpoint has been called, taking out 4 of the ADA, 4 of the Lovelace that were in there. And we get another transaction being validated. And then finally, after another 40 slots, we finish the contract with the last transaction. And then here, down there in the trace, there's like a more detailed log showing a lot of the internals of the emulator. So if anything goes wrong, you will see the information there. Now let's go back 1 second. Let's see what happens if we don't wait long enough. So if we only wait for, let's say, 10 blocks. So I've changed the action sequence here to only wait for 10 blocks instead of 20 after the initial vest funds call. Okay, now there are only 2 transactions. And those are the same 2 that we had in the beginning in the other simulation. So the script output still logs the 8 Lovelace. But there's no other transaction, so none of the funds were taken out of the script. And that's the intention, because the vesting contract is supposed to keep all the funds until the time has passed that was specified. And this is where we can use the the trace here, because now we can see an error message. Contract instance stop with error, cannot take out the value that was requested. For the maximum is value 0. So it means at this point, slot 11, we're not allowed to take out any value, and at least 8 lovelace, so the initial amount must remain locked by the script. So here we see the reason why nothing happened after that. So the contract instance stopped with an error, and wallet 1 stopped processing the events that happened, and it didn't even attempt to submit a transaction because that transaction would have been invalid. So we can play around with different settings here for the vesting contract. There's a final, another interesting contract that we're looking at, and that is this data contract. And this is one. So it's a simple contract, similar to Hello World, but it is one that actually creates a transaction and a script output. So this is like the basic scaffolding for a real script that goes on the chain. And I'm not going to go into the code that much because there are tutorials for that. I just want to have a quick look at the simulation. So again, we have some samples, some demo simulations here for this data contract. One is publish and redeem, which calls the publish and the redeem endpoints on 2 different wallets and the wait actions that are required. So let's look at that. Two transactions. One's the initial one, and then here we lock some funds in the script output, in the script that was created by the contract. And now we would have expected there to be 3 transactions because we called the publish endpoint, and afterwards we called the retrieve endpoint. And retrieve was supposed to unlock the funds here from this script, but that didn't happen. So if we scroll down to the logs, we can see here now that the validation of the transaction failed. And this is how the emulator shows any transaction errors, any invalid transactions that are sent to the chain. So in the live environment, with the real network and the real node, you wouldn't get this kind of feedback. If you were to send an invalid transaction to the network, it would just be rejected. But here we can see the reason why it was rejected and any kind of logging or anything that happened during execution of this. So that's another way that the simulator is quite useful, because we can use it to test transactions and get more detailed feedback from the node than we would in real life. And just quickly see where the error comes from. Here, line 35, it says there's a call to error, and this is the code, the script that is run. It says here, please provide an implementation. So you can extend these data types, and they put in the function that actually validates the output. But this here is always going to fail. And we just saw what the failure looked like in the simulator. Let's look at the other simulation that we have in this data contract. It's called pay to wallet. And as the name suggests, this only includes the pay to wallet action. And that action is independent of any contract-specific endpoints. Pay to wallet is always available, just like in a real setting, we could always make a payment to another address, to another user, independently of any contracts or apps that are running. Okay, this one produces a simulation with 2 transactions. And here we see what the pay-to-wallet transaction looks like. We use the funds that are owned by wallet 1. 24 of them go to wallet 2 and 76 go to wallet 1. So we can use these pay-to-wallet actions to transfer any kind of funds or tokens or whatever that we have in our examples. Now for the final contract that we're going to look at in this video is the crowdfunding one. And crowdfunding, that's always been our first example or prime example of a Plutus contract. And so it makes sense for it to be included in this iteration of the playground. And it does have a campaign built in. Now, if we evaluate this, we'll see that the blockchain here has 3 transactions that happen in the first slot. They all happen at the same time, and these are the 3 contributions to the campaign. So we start the crowdfunding campaign, and then interested parties can pledge money to the goal of this campaign. And in the simulation that we had, there were 3 submissions to the campaign, and they all happened at the same time. And this is also an improvement that wasn't possible earlier in the older version of the playground. Now we can actually have things that happen at the same time without waiting for the next slot to pass. Just as a little side note. So we can build much more realistic simulations than we could before. So there are 3 contributions, and then the final transaction here spends the 3 script outputs and gives them to wallet 1, which is the owner of the crowdfunding campaign. And that concludes the tour of the new playground. There's much more to see. So we have some new tutorials, some other sample contracts to check out, and they all have built-in simulations. So have a look around, try out all the scenarios that we've put in, and I'm excited to see what you're going to build with it.